My name's Trevor Londt. I got that right. I'm from Victoria University of Wellington in New Zealand, and I'm part of the Evolutionary Computation Research Group there. I'm going to present our work on evolving character-level DenseNet architectures using genetic programming. This work is related to trying to improve deep neural networks, particularly CNNs, on text classification tasks. So when you use CNNs or convolutional neural networks on text classification, there's primarily two paradigms that you can take. You can either use a word level approach or a character level approach. A word level approach will use word models, for example, word2vec or glove, where you have vector representations which encapsulate similarity between words. And this approach is actually very effective, and we've got some excellent results from it in our field. They do have their shortcomings. One of the problems is you have to have a word model that's appropriate for the language that you classify. And of course, for the bigger languages, that's not a problem. For lesser known languages, it can be an issue. And then there's a problem of out of vocabulary words. And of course, one of the biggest problems is you have to pre-process your text data, and that's quite a costly activity. The other approach is a character level approach. That's where you treat the text as a raw signal, no different to how you would treat an image or a sound signal. The text is encoded in a one-hot format, so it's a very simple representation. But these neural networks, these character level neural networks have excellent properties or advantages, and that's that they are resilient to noise. So you can have misspelled words, and with enough data, it'll pick that up. And they've got, in general, very small memory footprints, which makes them quite useful for mobile devices, as an example. And then, of course, the big positive is that you don't require any pre-processing of the text data. Unfortunately, compared to a word level approach, they're not as accurate. So they do have a bit of a limitation. And that's the limitation that we're interested in looking at. Excuse me a second. So as you saw there, the filter, it just goes across the quantized text, and it's one temporal convolutions. Now, the current state of the art for character level approaches is densely connected networks, or otherwise known as DenseNets. They've had excellent performance in the image analysis field, and recently they've been applied to text classification for character level models. They're quite good. They encourage feature reuse, and they allow, because you pass on each connection to the next layer down, it allows better gradient flow. So you can go quite deep with these neural networks. And they approach a similar accuracy to word level models, but they're not quite there. The problem is there hasn't been enough research to determine what's the optimal depth or width, and very little research with hyperparameter tuning. But in particular, we're quite interested in the depth problem. Because with image, the deeper you go, generally the better feature representation you can get. Whereas with text, especially with the character level, it hasn't really shown that. And designing these neural networks obviously are very difficult, and training them from scratch takes a lot of time. And it's basically an NP hard problem. And that's why we look at evolutionary computation to try and help us solve these problems. So there's been a lot of success using evolutionary deep learning to evolve image networks for image classification tasks. And motivated by this, we want to apply to evolve networks for text classification. In particular, we've chosen cellular encoding. It's from the 1990s. It was used to evolve multi-layer perceptrons, in particular nodes and weights and biases. But we've adapted this to be able to evolve CNN models. And there's two operations that we're primarily interested in. It's a sequential split and a parallel split. A sequential split adds kind of like depth to the network, and a parallel can include width. And when I say width, we can add or increase the number of filters down the network. And genetic programming is an excellent fit for cellular encoding. And we use that to facilitate crossover and mutation operations. So we defined what a convolutional block is. It's standard in the literature. It's a batch normalization operation followed by a ReLU activation function, and then a temporal convolution operation. Then we take these convolutional blocks and we chain them in a sequential chain with dense connections, and we define that as a dense block. Now, this dense block is analogous to a cell in cellular encoding. So it's these dense blocks that we're going to be operating on. So a quick visual representation of how the algorithm works. We use depth first, and you can see in step one, we have the S symbol there where our program counter is pointing to. And if you look at the phenotype, we start with the initial dense block or cell, and the input text comes in, and we have a classifier at the end. And then after we've executed, as you can see in step two, the S symbol, which is a sequential split, you can see that we've added another dense block at the bottom of step two in the phenotype, which has added an additional 5 layers to the network. Now that 5 layers comes from this decorator flag up at the top there on the genotype in step two. It's basically just an input parameter to say, when you do a split, take this integer and add so many layers to it. Similarly, in step three, you could see an example in the genotype when we do a parallel split. Now, a parallel split, if you look at the result in the phenotype, we've added another dense block to the right of the left dense block, and we've added a depth of 3. Now, that 3 again comes from that decorator flag. Now, note that we're increasing the width of the network because each of those dense blocks will have their own number of filters. And then, of course, in step number 4, after the blue S symbol, you'll see that again, we've added another depth of 3. Now, what's nice about using this approach with cellular encoding, it grows the network in a very organic manner. So you can get very unconventional CNNs. And it gives a good varying degree of width and depth. So with our experiment, we tested on 2 benchmark datasets. They're commonly used for character level architectures to test against. It's AG News and Yelp Reviews Full. AG News is considered a small data set. It's reasonably easy to model, and Yelp Reviews Full is a larger data set, which is quite difficult. The current state of the art is in the mid-60s. We only use 25% of the data set. The reason for this is because these, as I said earlier, these networks are very computationally expensive. We run for 30 runs. We do 10 epochs per candidate architecture that we train. And we use a low number of generations and population size of only 20. However, this is comparable to most EDL approaches in the image analysis field, again, because of the computational cost. Remember that we're training these networks up from scratch because we're just interested in the architecture and the topology, so there's no transfer learning. We choose a tournament selection size of 3 and a simple single point crossover and a uniform mutation operator. On the left is the training response for AG News. You can see that the neural net or the architecture converged really quickly within 8 epochs, probably closer to about 4 or 5. This response is typical of the current state-of-the-art models, so an iterative validation accuracy of 93.26%, which is actually very good. And on the bottom here, you see with this heat map, this represents all the models that were evolved over the evolutionary history. And this current best model that was found is on the bottom there with the lime square. It's approximately 5 parallel operations and a single sequential operation. Now, it implies that the models has a fair amount of width to it relative to depth. On the right-hand side, you can see the training response on the Yelp Reviews Full data set. And you can see straight away that the model started to overfit also with approximately 8 epochs. Now, this training response is also characteristic of the current state-of-the-art handcrafted models. It's a very difficult data set to model, but evolutionary computation was able to find some models that are still performant. Looking at the...
Trevor, sorry for interrupting you. I'm not sure if you are looking at the chat. 1 minute more, okay? We really have to. Okay.
Yeah. So just quickly at the genotype, that's the best genotype and the best phenotype. As you can see, as I said earlier, the model is definitely wide, not particularly deep. The test results, we're very close to the state-of-the-art manual design models, but they're much smaller models. The parameters are particularly small. And in conclusion, we've shown, we believe GP's got good potential, especially with the cellular or indirect encoding. And we believe we should look at width as further research. We're going to implement compression and, of course, parameter tuning for the learning rate schedule to prevent overfitting. But as this is only a 10-minute talk, please look at the paper for details, and welcome for questions and comments at the poster session. Thank you very much.
Okay, Trevor, unfortunately, we don't have time for questions here, but during the poster session, you can approach Trevor and know a lot more about this amazing work. So with that said, let's move along. Congratulations, by the way, clap, clap, clap.